My name is Sankirtana and I'm from CSC F section and my roll number is 24951A05Z5 and my topic for the AAT is Virtual Memory Simulator with Page Fault Detection. Introduction to Virtual Memory Simulation. So, virtual memory allows systems to use disk space as an extension of RAM. Virtual memory simulation is a technique used to model and analyze the behavior of virtual memory systems. It involves creating a software based representation of a computer's memory hierarchy, including main memory and secondary storage. There are some key components. Memory Management Unit maps virtual addresses to physical addresses. Data structures used by the MMU to manage memory algorithms. Strategies for deciding which page to evict from main memory. Benefits. Virtual memory simulation helps optimize memory usage and reduce waste. Simulation enables testing and optimization of memory intensive applications. Virtual memory simulation allows developers to test and debug memory related issues without hardware. Applications. Virtual memory simulation is used to test and optimize OS memory management. Simulation helps optimize memory usage in resource constrained systems. Virtual memory simulation is used to optimize memory allocation in cloud environment. This presentation introduces a virtual memory simulator with page fault detection features. What is virtual memory? Virtual memory is Virtual memory is a memory management technique used by operating systems to provide an abstraction layer between a program's memory request and the physical memory available on the computer. Virtual memory provides a logical address space decoupling programs from physical memory constraints, divides memory into fixed size blocks for efficient management. Pages are swapped between main memory and secondary storage as needed. Virtual memory allows programs to use more memory than physical available. Each program has its own isolated address space, improving security. Virtual memory optimizes memory usage by allocating it on demand. How it works: a program requests memory from the OS. The OS allocates virtual memory pages to the program. The MMU translates virtual address to the physical address. If a page is not in the main memory, the OS swaps it from the secondary storage. It improves system stability and multitasking capabilities. Components of virtual memory system. There are some components of the virtual memory system. A virtual memory system consists of several key components that work together to manage memory efficiently. The first component is Memory Management Unit. It translates virtual addresses to physical addresses, and it also handles page faults and memory protection. The second component is Page Tables, data structures used by MMU to manage memory mappings. It also contains page frame numbers, protection bits, and other attributes. Third one is page replacement algorithms, strategies for deciding which pages to evict from the main memory. Examples are least recently used, FIFO, first in, first out, and optimal. The fourth key component is page fault handler. It handles page faults by swapping pages between main memory and secondary storage. It updates page tables and MMU accordingly. The fifth key component is secondary storage. Provides additional storage space for pages not in the main memory, typically implemented using hard disks or SSDs. The sixth key component is virtual memory cache. A cache of frequently accessed pages improves performance by reducing page faults. These components work together to provide an efficient and effective virtual memory system. The disk acts as a secondary storage for the pages not currently in the RAM. Purpose of the simulator. There are some purposes of the simulator. The purpose of the simulator is to model and analyze the behavior of the virtual memory systems. The simulator models how virtual memory manages pages during program execution. Test and evaluate different page replacements algorithms and memory management strategies. Analyze the performance of virtual memory systems under various workloads and configurations. Optimize system design and configuration for improved performance and efficiency. Serve as an educational tool for students and professionals to learn about virtual memory. The simulator provides a controlled environment to experiment with different scenarios, allowing users to gain insights into the complex interactions within virtual memory systems. The primary goal is to detect page faults and analyze their impact. Key features of the simulator. The key features of the simulator are: the simulator has several key features that makes it useful tool for modeling and analyzing virtual memory systems. Configurable memory hierarchy. It allows users to configure the memory hierarchy, including main memory size, page size, and secondary storage size. Multiple page replacement algorithms. Supports multiple page replacement algorithms, including LRU, FIFO, and Optimal. Workload generation allows user to generate workloads with varying characteristics such as page reference, patterns, and memory access frequencies. Statistics collection collects statistics on page faults, memory usage, and other performance metrics. Provides visualization of memory usage and page fault patterns. Experimentation allows users to run experiments with different configurations and workloads. These features make the simulator a powerful tool for understanding and optimizing virtual memory systems. It also provides the insights into page replacement algorithms. Page faults explained. A page fault occurs when a requested page is not in physical memory. A page fault is an exception raised by the memory management unit when a program attempts to access a page that is not currently in the main memory. Types of page faults. Minor page fault. The page is already in main memory, but the MMU page tables is not aware of it. Major page fault. The page is not in the main memory and must be retrieved from secondary storage. Page fault handling. MMU raises exception. The MMU raises a page fault exception when it encounters a missing page. OS intervenes. The operating system intervenes to handle the page fault. Page retrieval. The OS retrieves the required page from the secondary storage. The OS updates the page table to reflect and the new page location. The program is restarted from the instruction that caused the page fault. Page faults can significantly impact system performance, making it essential to minimize them through effective page replacement algorithms and memory management strategies. How the simulator detects page faults. It is checked if the requested page is present in the current frame table. If the page is missing, a page fault is registered. The simulator then initiates the page replacement processes if needed. Page replacement algorithms. Common algorithms include FIFO, LRU, and optimal replacement. The simulator allows users to select and compare different algorithms. Efficient algorithms reduce the number of page faults. Simulator architecture overview consists of modules for memory management, page fault detection, and user interface. Uses data structures like arrays or linked lists for page and frame tables. Incorporates logic for page replacement and fault handling. User interface design provides options to input page request sequences, displays real-time status for pages in memory, visualizes page faults and replacements with clear indicators. Workflow of the simulation. User inputs sequence of page requests. The simulator processes each request sequentially. It logs page hits, page faults, and replacements during execution. Analyzing the results. Outputs include the total page faults and hit ratios. Users can evaluate the efficiency of different algorithms. The visualization aids in understanding memory management behavior. Practical applications used in educational settings to teach virtual memory concepts, assist developers in optimizing memory management strategies, helps in designing more efficient operating systems. Limitations of the simulator simplify certain real world memory management complexities, may not account for all hardware specific behaviors. Performance depends on the accuracy of the input request sequences. Future enhancements incorporate multi-threaded processors simulation, add support for different page replacement algorithms dynamically, improves visualization with animated memory operations. Example scenarios. A sequence of page requests is processed step by step. The simulator detects page fault when pages are missing. It demonstrates how different algorithms manage page replacement. Benefits of using the simulator enhances understanding the virtual memory management, allows experimentation without hardware limitations, supports learning through visual interface interactive feedback. Summary to the key points. Summary to the key points. Virtual memory simulation helps analyze page fault behavior. Virtual memory, a memory management technique that provides an abstraction layer between program's memory requests and physical memory. A page fault, an exception raised when a program accesses a page with not in the main memory. Strategies for deciding which pages for evict main memory. The simulator the simulator is a tool for modeling and analyzing virtual memory systems, allowing users to test and evaluate different configurations and algorithms. Conclusion. Implementing a virtual memory simulator with page fault detection offers valuable insights. In conclusion, we can talk that virtual memory is a crucial component for modern computer systems, enabling efficient use of memory and improved performance. Understanding how the virtual memory works, including page fault and page replacement algorithms, is essential for optimizing system design and configuration. The simulator provides a valuable tool for exploring and analyzing virtual memory systems, allowing users to gain hands on experience with insights into the complex interactions within these systems. Continued development will enhance its usefulness and accuracy. These are some of the references. Thank you.